Let's review again what we're working on at this point in the videos. Well, we've already figured out the rules for drawing legal resonance arrows, and now we're going over a couple of rules for making sure that you're drawing significant resonance structures. We don't want to bother drawing any resonance structures that are completely insignificant. Well, for example, we've learned don't bother drawing resonance structures with 3 or more charges. Those are almost always completely insignificant. I'd like to go over another rule now that helps you to draw only the significant resonance structures. And this has to do with this transition of moving a pi bond into a lone pair. Now, up till now, we've seen that this is kind of, in a sense, the easiest transition to make. We've learned that making a pi bond is very dicey. Anytime you make a pi bond, you have to make sure you're not exceeding an octet. But we've been much more lackadaisical about forming lone pairs. We know that forming a lone pair cannot exceed an octet. However, it turns out that even though this transition is always, is generally speaking always legal, it actually fairly often would give you a very insignificant outcome. So how can we make sure that we're only doing this transition when it's going to give us a significant resonance structure? Well, it turns out that generally speaking, as a rule of thumb, there's only 2 good reasons why you would ever want to form a lone pair. There's only 2 good reasons to form a lone pair. So let's write down what those 2 good reasons are. These are, generally speaking, the only 2 good reasons to form a new lone pair. There's only 2 good reasons to form a new lone pair. First of all, if it puts the electrons onto the more electronegative atom, that's a good reason to form a new lone pair. Or if it makes room for a new pi bond. If you don't have one of these 2 reasons, then you shouldn't bother forming a new lone pair. It would almost always be completely insignificant. So does it seem that this is going to give us a significant resonance structure? I hope that you paused the video and gave that some thought. Try to give some thought to each of the problems that we're posing. Well, we are forming a new lone pair here. We don't need to worry about exceeding an octet when we form a lone pair, but now we have a new issue. We know there's only 2 good reasons to form a new lone pair. One of them is to move the electrons onto the more electronegative atom. Well, that's precisely what we're doing here. Notice that this pi bond is being shared between the more electronegative oxygen and the less electronegative carbon. So right now, these electrons are being shared between a less electronegative atom, the carbon, and a more electronegative atom, the oxygen. Well, a good reason for forming a lone pair is to move those electrons totally onto the oxygen. So this is a good resonance arrow. It'll give us a significant structure because we're moving the electrons towards the more electronegative atom. Let's draw the resonance structure we're going to get. I hope it's very easy for you at this point to draw this new resonance structure. And you can see we really have moved the electron density onto the more electronegative atom over here. Well, that's a good reason to move electrons. Now, this structure is still less significant than this one. Why is this still less significant? Well, because it has charges. Charges are bad. And because this carbon has an incomplete octet. But even though it's less significant, it still is plenty significant enough to be worth drawing. Remember, it's okay to draw a less significant structure as long as it's not totally insignificant. Well, this is a long way from that. This is well worth drawing. In fact, in many contexts, it's very important to draw this resonance structure. This is significant even though we're forming charges because we're moving the electrons onto the oxygen, the more electronegative atom. So this is a good arrow. Is this going to be a helpful arrow? I hope you gave that some thought. Now the head of this arrow is pointing directly at this carbon, so we are taking this pi bond and making it into a lone pair. Pi bond to lone pair. We know there's only 2 good reasons for doing that, and one of them is to move electrons onto the more electronegative atom. But we're not doing that here. We're moving the electrons onto the carbon. That's the less electronegative atom. So this does not look like it's going to be good. And we're obviously not making room for any new pi bonds. We're not forming any new pi bonds back here on the oxygen. So this fails both of our criteria, so this is going to give us a completely insignificant resonance structure. It's a waste of time and just going to confuse us to draw this arrow and this resonance structure. Let's use redraw and modify to see what that resonance structure would look like. At the tail, we erase the pi bond. And then since the oxygen is losing the pi bond at the tail, it ends up with a positive charge. At the head, we're going to put a new lone pair on this carbon, and since this carbon is at the head, it's going to get a negative charge. Well, you can see what we've done. We've moved the electron density away from the oxygen and towards the carbon. But why would we want to do that? It's the oxygen that wants the electrons more. The carbon doesn't want the electrons more. So even though this is legal, this is perfectly legal, it's so totally insignificant, it's really a mistake to draw it. This is not going to play any significant role in determining the characteristics of this molecule. So we shouldn't really bother drawing this in the first place, and we shouldn't bother drawing this arrow. So I hope it's clear now what it means to move the electrons onto the more electronegative atom. This would be a case where we're moving a pi bond into a lone pair on the more electronegative atom. But we would not, and this is a case where we're moving the pi bond into a lone pair on the less electronegative atom, which is a mistake. We wouldn't want to do that. So this is a helpful, significant arrow, and this is a non-helpful arrow that gives us a totally insignificant resonance structure. Does this seem like a helpful arrow? Well, notice that the pi bond here is between two carbons. Neither of those carbons is more electronegative than the other one, so it doesn't seem like we have any good reason for moving this lone pair, for moving this pi bond into a lone pair. We're certainly not making room for a new pi bond. We're not forming any new pi bonds. And because these have equal electronegativity, there's no reason to move the electrons up here. So this is going to give us a completely insignificant resonance structure. There's no point drawing it. How about this? Well, this is totally useless for the same reason. Because these two carbons have the same electronegativity, there's no point in moving the pi bond into a lone pair on either of those two carbons. And again, clearly, we're not making room for a new pi bond either. So this again would be completely insignificant, not worth drawing in the first place. It would be a mistake to draw this arrow. Do these seem like useful arrows? I hope you gave that some thought. Well, notice that over here we are creating a new lone pair. Now, when we're making a lone pair, the good news is we don't have to worry about exceeding an octet. So this is definitely going to be legal, but now we have to worry about whether this is going to be significant. Well, at first it doesn't look good because we're moving this lone pair onto the carbon, but this carbon is no more electronegative than this carbon. So what's the point of moving this pi bond into a lone pair? Well, here there is a point. Now we're making room for a new pi bond coming in behind. Notice that this arrow is going to be forming a pi bond. Well, we've got to be very worried anytime we form a pi bond. Anytime we form a pi bond, we have to be worried that we're not going to exceed an octet. And if we're forming a new pi bond, unless it's with the carbocation, if we're forming a new pi bond, it's got to be with an atom that's losing a pi bond. Well, that's exactly what we have happening here. We're forming a new pi bond here. That's okay. We're not going to exceed an octet because this carbon that's gaining a pi bond is also going to be losing this pi bond. So this arrow is okay. And this arrow also is perfectly reasonable now. So hopefully now you see what I mean by saying that it's okay to form a new lone pair if you're doing it to make room for a new pi bond. Here we're forming this new lone pair. Here we're moving this pi bond into a lone pair to make room for this new pi bond that's coming in behind. So this is a totally reasonable set of arrows to draw, and it's going to give us an important resonance structure. So now we've seen the two reasons why you would want to move a pi bond into a lone pair. Either to move the electrons onto the more electronegative atom or to make room for a new pi bond that's coming in from behind. Obviously, if the two atoms have the same electronegativity, if they're both carbons, say, then this reason could not possibly apply. So if the two atoms are both carbons or both the same, the only reason why you would make a pi bond into a lone pair is to make room for a new pi bond coming in from behind.